Hi everyone, my name is Cameron Barron, and I'm very excited to present my research today. This work was supported by Worcester State University's Dr. Isaacou Research Fellowship Grant and guided by my wonderful professor, Dr. Nada Al-Salami. Over the summer, I explored misinformation detection using machine learning within the Amazon Web Services cloud environment. Let's get started. The purpose of this project is to create a powerful tool designed to combat the misinformation that inundates our daily lives. In today's fast-paced digital world, false information can spread like wildfire, leading to confusion, mistrust, and even harmful decisions. By training machine learning models to detect what we commonly refer to as fake news, this tool aims to serve as a means of validating the information we encounter. At the heart of this project lies a simple binary classification problem. That means that the machine learning model assigns one of two possible labels to a piece of information, either 0 for fake or 1 for true. This type of problem is fundamental in machine learning for tasks like spam detection and fraud analysis, making it a perfect fit for tackling misinformation. To the right, you'll see graphs from external sources that underscore the significant impact misinformation has on our society. One striking finding from the Pew Research Center reveals that nearly two-thirds of Americans report experiencing a great deal of confusion when it comes to distinguishing factual information in current events. This confusion isn't just anecdotal, it's a widespread societal issue with real consequences. The second graph, from Statista, quantifies the reach of fake news articles. It shows that such articles garnered 1.4 million more interactions compared to the mainstream media stories during the same period. This highlights not just the prevalence of misinformation, but also its troubling ability to capture attention at an unprecedented scale. This combination of statistical evidence and a machine learning solution emphasizes the urgency and importance of this research. By bridging data science and societal needs, this project seeks to create a tangible impact on how we consume and trust the information around us. The data for this research originated from two separate CSV files, which were meticulously labeled and then combined into a single working dataset. This dataset contained over 44,000 articles, each enriched with key metadata including the text body, title, subject, and publication date. Notably, these articles were written between 2015 and 2018, a period of intense political activity in the United States marked by a highly controversial presidential election. This period was characterized by heightened political unrest, which not only amplified societal divisions, but also led to a significant surge in the spread of misinformation. The preparation of this dataset was not a straightforward task. The raw data underwent a rigorous process of analysis and extensive preprocessing to ensure its suitability for machine learning. The analytical phase involved several key steps. First, we checked for class imbalance, ensuring that both the fake and true classes were represented adequately for meaningful model training. Next, we analyzed the distribution of the subjects, gaining insight into the thematic coverage of the dataset. A bigram analysis was also performed to identify commonly occurring pairs of words, which provided a deeper understanding of linguistic patterns in both true and fake articles. Finally, we determined the typical length of an article, finding that the majority contained between 10 and 500 words, providing a baseline for text preprocessing. These steps were crucial in transforming the raw data into a format suitable for training machine learning models. By carefully analyzing and preparing the data, we laid a strong foundation for building models capable of distinguishing fake news from true news with precision. This dataset not only reflects the challenges of misinformation during that volatile time, but also provides a window into the language, topics, and trends of that period. Text preprocessing was one of the most intricate and challenging components of this project, as effective preprocessing ensures that the model is trained on the most meaningful version of the text. Many natural language processing problems demand a balance between thorough cleaning and preserving linguistic nuance, as overprocessing can strip essential context from the data. This process began with removing noise from the text, including stop words, capital letters, punctuation, HTML tags, and numbers, to allow the models to focus solely on meaningful content. Once cleaned, the data was split into training, validation, and testing sets, a critical step to evaluate model performance and prevent overfitting. For the long, short-term memory model, tokenization was applied to break the text into individual tokens, followed by a sequence padding to ensure all input sequences were of the same length, a requirement for this type of neural network. Meanwhile, for XGBoost, the text was vectorized using scikit-learn's TF-IDF, or Term Frequency Inverse Document Frequency Vectorizer. This method transformed the textual data into numerical representations by assigning importance to words based on their relevance and frequency within each article. Although additional preprocessing techniques such as stemming and lemmatization were considered, they proved counterproductive as the models performed worse when these methods were applied. This carefully selected approach struck the right balance, retaining the integrity of the text data while ensuring it was primed for efficient and accurate classification with the models. This diagram illustrates the proposed AWS architecture that was used to implement the project as a web application accessible to users. At the core of the system is IAM, Identity and Access Management, which facilitates secure access between the different components, ensuring seamless communication throughout the architecture. The front end of the web application is hosted by AWS Amplify, providing users with an intuitive interface. From there, user requests are routed through API Gateway, which serves as the bridge to the backend. The backend relies on Lambda functions, capable of invoking the appropriate machine learning model depending on the request. For data management, S3 plays a dual role by securely storing the initial dataset and handling the outputs produced during processing. The machine learning heavy lifting takes place in SageMaker, which is responsible for data access, pre-processing, model training, and ultimately hosting the trained models for inference. This setup was developed and managed within a Jupyter Lab notebook utilizing an ML M4 large instance with a TensorFlow 2 Python 3.10 kernel for the main workflows. For inference and endpoint hosting, an ML M5 extra-large instance was employed, ensuring robust performance and scalability. This architecture enabled the efficient integration of machine learning with cloud services, creating a streamlined and accessible solution for combating misinformation. In this application, we use two powerful machine learning models, XGBoost and bidirectional long short-term memory, or LSTM. Each model was chosen for its unique strengths in tackling the task of misinformation detection. XGBoost works by optimizing performance through the combination of weaker models. It builds upon them to improve accuracy with a strong emphasis on feature importance. By identifying and prioritizing the most impactful terms in our data, XGBoost helps us uncover the key features that differentiate true news from fake news. For model fine-tuning, we use random search, a method that explores a range of hyperparameter values to find the most optimal combination for the model. On the other hand, the bidirectional LSTM model is a type of recurrent neural network designed to excel at sequential data like text. Its strength lies in the ability to learn not just from the beginning to the end of the sequence, but also in reverse, from end to beginning. This bidirectionality allows the model to capture richer context and dependencies in the text, which is crucial for understanding complex sentence structures and determining whether a piece of news is reliable. Together, these two models bring complementary approaches to detecting misinformation, with XGBoost focusing on feature importance and long short-term memory, leveraging the power of sequential data. When we evaluate the performance of both models, we see promising results based on a variety of metrics. For the bidirectional LSTM model, the accuracy stands at an impressive 97%. Additionally, the model's loss was closely monitored throughout the training process, and the low loss value indicates that the model was able to minimize error effectively, resulting in reliable predictions for the test data. On the other hand, XGBoost delivers even higher performance, with an accuracy of 99%. To assess this model further, we looked at key classification metrics, such as precision, recall, and F1 score, which are crucial for understanding how well the model distinguishes between true and fake news. The precision and recall values provide insight into the model's ability to correctly identify both true positives and false positives, while the F1 score balances precision and recall to give a more comprehensive view of the model's overall performance. To help visualize these metrics, we have included the confusion matrices for each model. These matrices provide the number of true positives, true negatives, and false negatives, offering a clear picture of how each model performed in categorizing articles as either true or fake. This is an example of testing the models using external data to assess their real-world applicability. In this case, the input article has an actual label of true. The LSTM model successfully classifies the input as true, demonstrating its strong ability to correctly identify accurate information. However, the XGBoost model misclassified the same input as fake, highlighting a potential weakness in classification for this particular example. This discrepancy between the two models shows that while both models perform well on the overall dataset, there can still be external instances where one model may outperform the other. It's important to recognize that no model is perfect, and understanding the nuances and limitations of each is crucial for future improvements. This is another example of testing the models with external data, this time using an input that has an actual label of fake. In this case, both the long short-term memory and XGBoost models correctly classified the instance as fake, demonstrating their ability to identify false information. However, after repeating these testing scenarios with both true and fake articles multiple times, a clear pattern emerged. The XGBoost model consistently leaned toward classifying inputs as fake, even when the input was actually true. At the time, I couldn't fully explain why this was happening, so I continued to study the data and analyze the results in greater detail to understand the underlying cause. To further understand why the XGBoost model was misclassifying certain articles, I used latent dirichlet allocation, or LDA topic modeling, to analyze the topics in both true and fake news articles. The analysis revealed that true news articles often focused on political terms like president and Senate, while fake news articles were more likely to include words like Trump, party, and police, which can be more emotionally charged. One key issue I found was that the XGBoost model was heavily relying on the news source disclaimers, like Reuters, at the start of articles to classify them as true or fake. This caused the model to misclassify some articles, especially when the actual content didn't match the headline. When I added these disclaimers to the beginning of the article during testing, the XGBoost model incorrectly labeled some articles as true, even when they were fake. In contrast, the LSTM model didn't fall into this trap. It was able to look beyond the disclaimers and focus on the actual content of the article, leading to more accurate classifications. These results highlight an important difference. While the XGBoost model was good at identifying patterns, it sometimes overfitted to external clues like the news source disclaimer. On the other hand, the LSTM model was better at understanding the article's content, which helped it make more reliable predictions. Here, we have a true news article that the LSTM model correctly classifies as true. It looks beyond the content and understands the full context of the article, accurately identifying it as genuine news. However, the XGBoost model which was influenced by external patterns, mislabels the article as fake. The reason? This article does not have a news source disclaimer, and the XGBoost model relies heavily on finding this pattern. Without it, the model struggles and incorrectly classifies this article as fake. Now, let's look at the same article, but with a news source disclaimer appended to the beginning. The LSTM model still correctly classifies the article as true because it focuses on the content, independent of the disclaimer. However, the XGBoost model has now changed its classification to true as well. This time, the presence of the disclaimer, which the XGBoost model heavily relied on, leads it to classify the article as genuine. This shift in behavior highlights how XGBoost can be overly reliant on external cues, like the disclaimer, instead of purely focusing on the content of the article as it should. In summary, the LSTM model outperforms XGBoost in key areas. It shows high accuracy, minimal overfitting, and strong generalization abilities, making it ideal for real-world applications like this one, where reliable classification of external data is crucial. On the other hand, XGBoost is prone to overfitting and struggles with generalizing to new data, especially when it depends on specific features like news source disclaimers. While both models perform well on internal data, LSTM's ability to handle biases and generalize makes it the better choice for this circumstance. Insights from LDA topic modeling revealed that XGBoost's reliance on familiar sources, much like human bias, limits its accuracy in diverse contexts. Therefore, for implementing the web app, LSTM provides the more reliable and adaptable solution. In the field of misinformation detection, there is still a lot of potential for further research and improvement. This study marks just one step toward a more robust solution, but there are several ways it can be expanded upon. One possibility would be to improve the XGBoost model by adding news source names as stop words during the pre-processing stage. By removing these terms from the model's vocabulary, we could test how this adjustment influences performance and generalization, especially in terms of recognizing bias related to source reliance. Another key improvement would be to complete the UI component of the project. This would allow users to make predictions directly from the web application, which currently remains a work in progress due to time constraints. Once completed, this functionality will enable users to interact with the model, providing practical, real-world applications for misinformation detection. Finally, an exciting avenue to explore would be the integration of multilingual capabilities. Expanding the model's ability to detect misinformation across multiple languages would broaden its utility and applicability to a global audience, offering a more comprehensive solution in the fight against misinformation globally. I'd just like to take a moment to thank Dr. Nada Al-Salami for her guidance throughout this project. This research was completed under the Dr. Isagu Research Fellowship Grant at Worcester State University, and I greatly appreciate the support I received in making this research possible. These references and sources were critical in shaping this research. Feel free to dive deeper into these resources if you're interested in exploring the topics of misinformation detection or the machine learning models that were used. Thank you very much for your time and attention. If you have any questions or would like to learn more about this research, please feel free to reach out. Contact information is provided here.